The analytical approaches of empirical modeling may be divided into three main common types. I'm sure there are many other types of analysis or approaches. The first one is the traditional curve fitting, which most engineers and manufacturers know, and that's why I have to start with that, to show you the difference between that and the true statistical modeling. The second one is a simple correlation analysis. We will discuss that as well in this chapter. And the third one is the regression analysis. Curve fitting. All engineers and manufacturers know what curve fitting is. All scientists and researchers know what curve fitting is. It is the analysis required to find equations of approximating curves that fit a given set of data. Except we hope that this data does not exhibit a great deal of scatter. In this case, the curve fitting procedure is a standard mathematical procedure. If the relationship is a straight line, then the best way to curve fit that is to find the slope and the intercept, and we can use these to develop the model or develop the XY relationship. Here is one relationship. Sometimes we may have a slight scatter in the data that will require a little bit of more effort in curve fitting, but the classic curve fitting does not involve scatter at all. When you have a pure curve fitting, when you have a straightforward linear relationship such as this one, we say that the correlation coefficient, that is the coefficient describing the strength of the relationship between X and Y, is 1. And we will explain that shortly. If you have some scattered, you may be able to roughly curve fit that and develop a deterministic relationship because you are really ignoring the scattered. In other words, just fitting the average values without consideration of any scattered. And in this case, you can do curve fitting by finding the slope and the intercept. And you have to be very careful here because the strength of the relationship will not be as good as the one with the no scatter that we've seen a minute ago. You can develop many relationships, and by doing that you may come up with some linear, with some quadratic, with some power functions that fit the data that you're dealing with. Quite often, well, we have to understand why we fit in data. We fit data. The whole process of fitting data is finding this constant that you see in this equation. After all, we have X that's variable, we have Y that's variable. We're changing X and we're looking at the corresponding change in Y. So what's a curve fitting? Curve fitting is finding the constants associated with the function in hand. Correlation regression analysis deal with variability, deal with the real world, deal with the scatter of the data. When I have a scatter like that, I tend to think about the best fit. So correlation or regression analysis still deal with curve fitting, but with a great deal of scatter. And that's why we put them in a separate category. Okay, because there is no deterministic issues here. Everything is random. X value can vary in any random fashion. And accordingly, Y may change in a random fashion as well. So when X changes randomly and Y correspondingly changes randomly, we have to do correlation and regression analysis. Another aspect before we move on is we have to understand the difference between correlation and regression. And of course, we will understand that as we cover examples and talk or proceed with this chapter. A correlation is merely a way to determine the strength of the relationship. That's all. While a regression analysis go beyond that. In addition to determining the strength of the relationship, it also develop or help us develop the relationship. Okay? So it's extremely important to understand that. Perhaps before we start the mathematical details, it will be useful to introduce the so-called correlation coefficient. A correlation coefficient ranges from -1 to +1. A +1 implies a very positive, strong relationship. And the -1 implies a very negative, strong relationship. So here is a strong negative correlation, and here is a strong positive correlation. However, as we go from -1 to +1, there is a value in the middle, which is a 0. And when you have an r equals 0, that implies no relationship, meaning that x can change as it wishes, but y will not respond. X can increase from low to high values, but you can see that the y is not really changing in any linear trend. So keep that in mind. We have the coefficient of correlation, or the correlation coefficient, as an index of the strength of the relationship. Before we get into the details of how we develop a relationship, there are two important criteria that mainly deal with two things: the database as well as the nature of the relationship. The first criteria of developing a relationship is that we have to use a practical range of values of independent variables, the x values. The second aspect is we have, as we developing a model or developing an equation, look at the linear effect or the nonlinear effect of the relationship. It's very important that we do that. There is no systematic way to do these things. This is where the analyst's judgment becomes extremely important. Let's look at the first factor, the plausible range of values of independent variable. If one have a set of data of x and y that can go, for example, the x value all the way from 2 to 6. You can see here this is the lowest value, but it can go as high as 6. And y is the dependent variable that will change as x changes. Well, suppose that one only dealt with the range of x values from 2 to about 3.6. So this is the range. And you can see here that as x increases, y increases in a very positive, very linear fashion. If one develops such a relationship, the obvious outcome will be a linear straight line, okay, with a large, high, positive correlation coefficient. Very good. Now remember, we only dealt with a small range, okay? Suppose, on the other hand, somebody else took the range from 3.6 to 4.2, just this set of data here, and decided to perform or develop a relationship for this. As you can see over this range, as x increases, y doesn't increase, doesn't change. It goes ups and down in a random fashion, but there is no trend. So in this case, this relationship will give us a constant trend of y with the change in x and a correlation coefficient of 0 or close to 0. Now, suppose somebody is looking at the last range here, that from 4.2 to 6. One can see here that we have a decreasing trend. And if somebody just used this set of data here, or the data that has this range only, with that scatter, one will find a strong negative correlation. This is why the first feature is extremely important. You must consider the entire range of data, especially the range over which in the future you will use the relationship to predict other values. If the one that performed the relationship over this range tried to use this relationship to predict the y value at x value here, there will be no way, because what this relationship is telling us is that there is a continuous increase in y with the increase in x. If the one tried to go backward, if he's using this equation here or this relationship here to predict the y value at x value below this range, one will find that there is either no change or of course prediction wise you will find always higher values of y because you're using this relationship. Okay, so you can see here that unless we cover this entire range, extrapolation or predicting the y value at some x values that were not considered in the range of the data that were used for the analysis will be impossible. Obviously, in a case like that, if one would use the entire range from 2 to 6, one will find that the relationship is essentially a non-linear relationship. And that takes us to the second issue, is that it is very important before you dare do any type of modeling analysis is to look graphically, if you can, at how the y changes with x. Even if you're dealing with multiple x values, it will be useful to look at two ways relationship between the y and the different x's. Here is a case where if you don't know what you're doing and you are not looking at the data closely, you can easily develop a relationship that is linear. The higher the x's, the lower the y, no matter what. That is because we did not see the data to start with. If we seen the data, we will see that we have an increase in the data in the initial part of x, and at higher values of x, we have a reverse in the trend, and that may imply a non-linear relationship. There are two types of regression analysis: the simple regression analysis and the multiple regression analysis. Simple regression means a two-way relationship, x and y. So we're trying to develop a relationship where we have one input variable and one output variable. In multiple regression analysis, we have multiple input, many independent variables, x1, x2, x3, and so on, and we have one output. So it's very important we know the difference between the two. Let's first take the simple regression analysis, or the linear model for simple regression. The general form of the linear model is as we see here: y equal beta 0 plus beta 1 times x plus an error term. Beta 0 is the intercept, beta 1 is the slope. The purpose of simple regression analysis is basically to estimate beta 0 and beta 1 in such a way that will minimize the effect of this error. In practical terms, we say we're trying to find the best fit. We're trying to find the best line that will go through the data, and the best beta 0, B0, and the best B1. So B0 and B1 are estimates of beta 0 and beta 1. So here is the real world, real data with the scattered. Our purpose is to estimate B0 and B1 that will actually give us the minimum error. That is what we call the least squares method. In a least square method, without getting into the mathematical details of the method, we're trying to fit a relationship of some form. We're trying to draw a line or a curve between these points at which the deviation from these points to the line or the curve are minimum. You see this deviation here? You see this deviation here? Our goal here is a minimum sum of the squares of this of these deviations, and that is the underlying meaning of least squares. So what's the best fitted curve? This is the one that's obtained at minimum sum of these deviations here. That is the curve or the line that result in minimum epsilon, indeed in an average epsilon of 0. And that is the line that will yield good estimates of beta 0 and beta 1, or good values of B0 and B1. Okay? So now we agree that the least square method relies on minimizing the sum of square of these deviations from the real point to the predicted or the line points. Actually, if we look at the top equation carefully and use the second equation here, okay, and try to rewrite it in such a way that we can get the sum of y corresponding to the sum of x, okay, then this is what we're going to get. Sum y equal b0 times n, because b0 is a constant, so really the sum of b0 is the number of observations we have times b0 plus b1 times the sum of x. If we multiply both sides of the equation, we will get, by x I mean, we will get sigma xy equal b0 sum x times plus b1 times sum x squared. These are the standard, these equations represent the starting point of any least square analysis. Our job is to use these equations to estimate the constant b0 and b1. These equations are commonly known as the normal equations of least square. Note that division of both sides of the first normal equation by the sample size or by the number of observations. Let's divide that. Let's divide the first equation here by the sample size. Sigma y over n will give us the y bar, the average of y. And sigma x over n will give us the average of x's. B0 will be divided by B0, n will be divided by n, will give us B0, and B1, okay, sigma x will be divided by n, which will give us the B1 x bar. This is the average equation, derived directly from the normal equation. That is if we want to fit the average against the average values. From these, we can obtain the values of the constant B0 and B1, as I said. And here is a mathematical form of finding the values of B0 and finding the values of B1. And these terms inside each of these two equations are directly obtained from the data that we have, from the x values and the y values we have. Before we go any further, let us define the correlation coefficient that we have reviewed earlier without any mathematical details. We already know the physical meaning of the coefficient of correlation. We know that the limits of it. We know what it means to have a perfect negative or perfect positive correlation. We know what happens when the correlation coefficient is 0. But now we're going to define it mathematically or statistically. The coefficient of correlation is equal to the so-called SXY divided by SX times SY. When we say S, as we always did, we mean a standard deviation. It's a sum of some form. So let's see this. Sx is a variance of x, or derived from the variance of x, or it is the standard deviation of x, where the variance of x, as we always known, is equal to the sum of the x values minus the average square divided by n. Very good. Y is also the variance of y, or SY, I mean, is the standard deviation of y, and this is derived from the square root of the variance of y, which is the sum of y, individual y, minus the average of y divided square divided by n. SXY is new for us here. It's not a variance. Well, it is, but it is an interactive variance, and that's why we call it the covariance of x and y. Okay? It is really the sum of xi minus the average of x's times yi, with the individual values of y, minus the y bar, or the average of y's, divided by n. Very simple. Okay? So we've just introduced the meaning of covariance. And it is that meaning of covariance that has made the correlation coefficient a very meaningful measure of the strength of correlation. Let's take an example. If I have x and y completely independent, meaning that x and y have no relationship. If that is the case, then the covariance SXY will be 0. And that is when we will have a coefficient of correlation of 0 or no relationship between the two. Now, consider on the other hand the case if x and y are completely dependent. And let's just put a function. Let's say x equal y. If x equal y, then SXY will be mathematically equal to SX times SY. And what's that going to give us? It's going to give us a correlation coefficient of 1. So that is the underlying concept of the coefficient of correlation, is the fact that we're dealing with a covariance of xy divided by the variance of x, or a function of the variance of x and a function of the variance of y multiplied. So now we know why r can be 0, r can be 1, and of course r can be negative 1 depending on the sign of the standard deviation of the covariance. This leads us to some of the features of the coefficient of correlation that we have to understand before we go further with the analysis. First of all, we have to understand, as we did already, that R reflects the direction of the XY relationship. As soon as we see the relationship, we see the trend, whether it is positive or negative or no, we know that our value will follow. Okay? Second feature, which is a common misconception, is that R may be insensitive to the intercept. In other words, you may have 3 lines that have basically the same slope but different intercepts, and they could have more or less the same R value. The key is R reflects the extent of the scatter. If you have too much scatter, R will be low. Here is a relationship of y, after we did the regression analysis, and we'll show that later to you, where y equal 2 plus 2x, but it exhibits a high scatter. The R value here is 0.9644. Okay? If I redevelop the same relationship with data like this of less scattered, yet the average at each xy of y is exactly the same as this one, meaning that I'm keeping the average value of y at each x value is the same, I will have the same linear relationship, but the r value will be much greater. Why? Because I have less scattered. Here is a case where we have no scatter and we will have a perfect r. So the r value is a good reflection of the scatter in the data, and that's extremely important to understand. Let's take an example now. Here is we have, of course, we're going to start with a very simple example here to demonstrate how we do the regression analysis manually. We will then go to Excel spreadsheet and we show you how this analysis can be done in a very, very short, in fact, fraction of seconds. What we have here are random values of x and the y value of y. The input here is fibers going to the textile process, and from these fibers we have the fiber properties, especially the strength of the fiber. We're making yarns out of these fibers, and we're looking at the strength of the yarn, and we're trying to see whether there is a relationship between the strength of the fiber, the strength of raw material, and the strength of the output product or not, or how this relationship looks like. Is it linear? Is it non-linear? And what's the strength of this relationship? These are all questions that the regression analysis can answer. And whether we can predict the y value at maybe higher values of x than this one or lower values of x than this one. Okay? Here is our x's, here is our y. Manually, the first step we do is to square each value of x and get a column of the square values of x's. Square the values of y and get a column of the square values of y. Multiply xy and get a column of the xy products. In other words, we are shooting for the variance of x, the variance of y, and the covariance. That's the essence of regression analysis, as you know. From this information, we can find the values of P0, the values of P1, the estimates values, as well as the coefficient of correlation. Let's take it one step at a time. The P0 is sigma y times sigma x squared. We have the sum of y's, we have the sum of x squared, minus sigma x, we have that, times sigma xy, we have that, divided by n times sigma x squared minus sigma x all squared, and that gives us the P0. The P1, you can see the equation here, and each term of this equation is also derived or driven from the table that we just showed you. So every single term in these two equations that are required to estimate B0 and B1 manually are obtained or is obtained from this very simple table that we developed. Okay. And once we know B0 and B1, we know the relationship. Y equal B0 plus B1 times X. So Y equal minus 5.4 plus 14.71, which is the B1, times X. Or the yarn strength, the output, equal minus 5.4, the intercept, plus 14.71, the slope, times the X value or the fiber strength. And this is simply telling us that we have a positive relationship with a negative intercept of YS or yarn strength and FS or fiber strength. I'm not going to discuss how we calculate the coefficient of correlation now, because there is more simplified ways to do that later on. But we will get to that. At this point of time, we were able to determine the intercept and the constant or the slope, meaning that we were able to write down the relationship, which is our goal at this point of time. How the R came out to be 0.94, I will explain that very shortly. Okay. Let's now look at some of the important issues associated with regression. These are the regression assumptions. These assumptions are very known to many people who have dealt with regression in the past. Existence, linearity, independence, or homoscedasticity, and then normality. Okay. Here is a relationship. A great deal of scatter in the x and the y data corresponding to each x value. When we say existence, what we mean by that is for a fixed value of the variable x, like 20 or 22 or 24, y is there, and it is a random variable with certain probability distributions. Okay. Linearity is that we are assuming a linear function. Okay? So this has to be taken into consideration to start with. When we do regression, linear regression, our assumption or our assumed model is a linear model. So that's very simple. Here is the random effects of the y values, which is the existence issue, and the linearity, as you can see here, is a trend that we assume to start with. And that's why it is possible, based on these assumptions, to estimate the average y, or to estimate the coefficients beta 0 and beta 1. The key of this equation that you see here is that this is different than the model. This is the mean of the y values. We don't see epsilon here, because epsilon here is now 0. Because the average of epsilon, the average of error term is 0. This is the general model. Okay. Independence. Independence in regression analysis, the values of the random variable y are assumed to be independent of one another. Okay, so having one value of y will not affect having another value of y. That's extremely important assumption when it comes to regression. Because obviously this assumption, or we should know that this assumption applies to almost any regression model. And later on it will apply obviously for multiple regression. When observations are not independent, when one observation can affect the other observation of y, there are special procedures that we have to follow. These such as the multivariate linear modeling and weight least square techniques, which are really outside the scope of this chapter here. But it can happen. If you're dealing with data that are periodic in nature or production data, quite often y1 and y2 may be dependent or may be related in some form. Homoscedasticity. Well, this assumption implies that the variance of y, the responsive variable variance, is the same for any value of x. And by the way, the term homo here means same. That's why we say homoscedasticity means the variance of y for any value of x is the same. Cedastic, on the other hand, is a Greek name meaning scatter. So we're saying that the scatter of y around any value of x is more or less the same. That's what we mean by the variance of y is the same for any value of x. Okay? The opposite word to homoscedasticity is heteroscedasticity. So hetero will be different. Homo will be the same. Finally, normality. Normality assumption implies that for any fixed value of x, y has a normal distribution. So if I collect enough values of y for a given value of x, I can construct a frequency distribution that follows the normal distribution. This assumption may be violated a little bit. In other words, quite often in practice, we don't deal with too many data. So really, if the assumption of normality is violated slightly, we can we can live with that. Now, if we know for a fact that the assumption of y is deemed unsatisfactory, that the assumption of y being normal, or the assumption of normality, is deemed unsatisfactory, then some transformation may be required. We may have to transform the data to some form, some functional form that can fulfill or satisfy the normality assumption. Of course, such procedure requires that other assumptions of regression, linearity, existence, and all of that be satisfied after the transformation effect. Now we deal with a very important issue. That is the standard error of estimate. We have introduced the standard error early on in chapter 3 as an adjusted standard deviation of mean. And it is a function of the standard deviation as well as the sample size. Well, this concept happens to come back and haunt us again in regression. What we are fitting here, we are fitting a line, a single line that passes through all the points. But this single line may be associated with confidence, upper limit for this line and lower limit. And in order to obtain the upper and lower limit of confidence for any regression line, we have to estimate the standard error or calculate the standard error of estimate. That's the SYX here, which is basically defined by the sum of the individual observations minus the predicted y values squared divided by n. So it looks like a variance, a standard deviation definition, but this time instead of the average y, we're talking about deviation for, or the difference between actual values and predicted values. And of course, we know what predicted values means now. It is the value using the constant b0 after we calculate it, using the b1 after we calculate it, times the x. We also should know that the deviation or the difference between the actual values and the predicted values is the error term. Remember, after all, the least square method was designed to minimize the sum of square of this error. A modified standard error from this equation here may be put as follows. So remember, this is the SSE, or the sum of square of errors. If I'm dealing with a small sample, then the estimated standard error should be determined from this equation, where we have n sample size divided by n minus 2 times the standard error that's classically determined by the previous equation. Accordingly, we can put a general definition of the square of the standard error as 1 over n2 times the sum of square error. Sum of square error. Well, if you recall, we were able to get the sum of square error from the so-called analysis of variance, which we discussed in the previous chapter, which we will have to introduce in association with regression, because it's a part of the underlying concept of regression to do analysis of variance. That is to partition the y variable, the dependent variable, into the different sources of variation that may be affecting the y variable. So this is the definition of our standard error, or the square of the standard error. And of course, you can see that all these values can be obtained manually. We have the b0, we have b1, we know how to calculate them. We have the sum of xi, yi, we have the sum of yi squared, we have the sum of y, everything. In fact, here it is. Okay. If we can calculate the standard error, then we can easily establish confidence on our fitted line. So instead of just showing a line, we can also show an upper and the lower limit that are plus or minus some value times that standard error from the regression line. So not only that we can develop a regression line and we can plot it, we can also develop a confidence, meaning that, well, okay, the predicted value at x of 22.5 may be here, right? But it may also range from here down to here. The predicted value at 25 may be here, but it may also range from this point to this point. That's establishing confidence on our regression line, on our predicted values, actually. Very good. This issue, this immediate issue, introduces us to the analysis of variance, as I just mentioned. The total variation of the response variable, y, is defined by the sum of the square of the individual values of y minus the average. We can mimic this equation a little bit, this top equation here, okay, to lead us to this equation, meaning that the total variation or the sum of the squares of the deviation of individual values of I from the average would be equal to this sum term and this sum term. Now let's investigate or examine each sum term. This sum term here is the difference between, or the square of the differences between the individual predicted values and the average. We will call this, in the analysis of variance associated with regression, as the variation due to regression. If we look at the other term, this is a very familiar term. This is the square of the difference between the actual observation and the predicted observation, and that's what we called early on, in fact shortly, the error term. So now we can partition the total variation in y into variation due to regression, this deviation from the mean value of the y values, and, or the mean value of y, and sum of square of error or residuals. Let's demonstrate that graphically. I have some points here that exhibit some scattered. At any x value, there is a y value. So if I use this concept here, that's the sum of square of y, to be equal to the sum of square due to regression plus the sum of square of error, the way we can reveal that graphically is as follows. First of all, we have the fitted line. Second, we have the point, any point at the fitted line is estimated y. That's the y hat, which we know where it came from. An estimate of beta 0, remember that was the b0, plus an estimate of beta 1, which was b1 times xi. That creates a difference here between the actual value and the predicted value. That deals with this term here, the error term. And of course, each point will follow the same concept. Very good. On the other hand, all the y values have an average. In fact, the average value of y is here. You can see it here, right? That means the predicted value is also deviated from the average of all y's. And that's the second term in the equation. So you can see now that the concept of analysis of variance in regression is about partitioning the variation in y, the overall or the total variation in y, into two components. One component is the deviation from between the actual value and the predicted value. The other component is a deviation between, or the difference between, the predicted value and the average of all y's. And that gives us the total deviations. Now we introduce a new term a very commonly known term, the so-called coefficient of determination, or R squared. Earlier in this chapter, we introduced R. Well, R squared is the square of R. So why are we dealing with the square of R if we already know R? Well, as we will find out, R and the R squared have two different meanings. R was derived from the covariance xy divided by the x standard deviation or variance times the y standard deviation or variance. In fact, if we square the covariance, it will be equal to sy, if s squared y times 1 minus R squared. They're just mimicking the equation. Okay? So the R squared derived directly from R will be equal 1 minus the sum of the deviations or the differences between the actual value and the predicted value divided by the sum of the square of the differences between the actual value and the average. Now we're closing the R squared with the analysis of variance concept that we mentioned a minute ago, because we have mentioned this as being the error term, and we have mentioned this as being the regression sum of square. So if we rearrange this equation a little bit, we will find that this equation lies right in the heart of the ANOVA concept. Indeed, the R squared, by rearranging this equation, will be equal to the sum of the squares of the differences between the predicted values and the mean, and over the sum of the squares of the differences between the actual values and the mean. That is the ratio between the explained variation by the model and the total variation of the model or the data. So R squared will give us an index of how much X explains Y. That's a different way to define R squared. We know that the explained variation or the regression variation is equal to the sum of square of the Y, the total sum of square, minus the error, right? Divided by the total variation, which is the sum of square of Y. So how much is explained by the X variable toward Y is defined or determined by the R squared. The concept of R squared, or coefficient of determination, will become even more important when we deal with multiple regression, because in case of simple regression, really both R and the R squared are quite correlated, and they both mean basically the same thing, the strength of correlation. But the R squared, when we go to multiple regression, will start to give us some information about the relative contribution of different variables to the overall model. Since R ranges from -1 to +1, going through 0, the R squared mathematically will range from 0 to 1. With 0 means zero contribution, and 1 means perfect contribution of X to Y. So this slide here summarizes everything that we need to know about the coefficient of determination.